Good afternoon, all of you. My name is Nitin Tomar, and I am a fourth year PhD student in the Department of Mathematics. So, in today's lecture, we'll see some indirect methods for solving a system of linear equation, mainly the Jacobi method and the Gauss-Seidel method. So, and these methods are called iterative method for solving linear system. Iterative methods for solving linear systems. See, we have already seen Gaussian elimination, and what did we do there? In the Gaussian elimination, you have, so if A is invertible, for an invertible matrix A, let's say of order of size n cross n, and a vector B in Rn, we want to solve this system Ax equal to B. Now this system gives us, okay, we'll discuss Gaussian elimination already, so I will not write here. So what does solving a system mean? It means if you have an invertible matrix, because we are restricting ourselves to invertible matrices. So for an invertible matrix and a vector B in Rn, we want to solve the system Ax equal to B. Now, what does it mean? What does it mean? We have already seen this many times, but let us revise in a bit. So if A is of this form, and let's say X is the unknown vector, and B is the vector that needs to be given. So solving this system means find a value of x, find the value of this x1, x2, xn such that Ax equal to B. Now what does it mean? If you multiply the matrices, so it will give you some system of equation. It will give you n many equations. Oh, sorry, here it should be x1. Yeah. So this is the given system of equation. Now you have to find value of x1, x2, xn such that this n many equations are being satisfied. And we know because A is an invertible matrix, we have assumed A is an invertible matrix, then this system will have a unique solution. Remark, okay, as a remark. Since A is an invertible matrix, the system Ax equal to B has a unique solution. And what is that unique solution? That unique solution is given by x equal to, because A is invertible, so A inverse B. That is my unique solution. Yeah. So the question arises how to find, because finding an inverse we have already seen in previous classes that finding an inverse is a costly process, and we have seen why. It involves a lot of operations. So is there any method that can, via which we can easily solve this system? Now we know Gauss elimination is one of them, and it is a direct method in the sense that a solution is obtained after a single application of Gaussian elimination. Now once a solution has been obtained, Gauss elimination method offers no method of refinement. So, and also the Gauss elimination method is sensitive to rounding error. This we also have seen in one example. Now, so these numerical techniques such as Gaussian elimination is not much applicable. Okay. So we commonly use a more iterative method, and in this section we'll look at two iterative methods for approximating the solution for a system of n linear equations in n variable. So the first method is the Jacobi method. So let me write what I just so we will see two iterative methods. First is Jacobi method, and second is Gauss-Seidel method. So we'll quickly do, because all these things have been covered by in lectures. So the first thing is the Jacobi method. So because we'll be working, so this method makes two assumptions. Number one, the system given by Ax equal to B, this system has a unique solution So this condition, if we consider invertible matrix, so this condition will hold, right, as seen in the above remark. So in the bracket we write, oh okay, this condition is true this condition is always true if A is an invertible matrix. If A is an invertible matrix. Now, second thing is the coefficient matrix A the coefficient matrix A has no zeros on its main diagonal, on its main diagonal. So that is A11, A22, all these entries are non-zero, are non-zero. So we will see how does it. So a quick remark or a note. If some entries, if any of the diagonal entries are 0, then rows or columns must be interchanged to obtain a coefficient matrix to obtain a to obtain a coefficient matrix that has non-zero entries on the main diagonal. Yeah. Okay. So for example, we'll just see what do we mean by this note. If you have a system like this, 0, 1, simple system, So this matrix A is invertible, right? Why? Because determinant of A is not 0. So the condition 1 of Jacobi method is satisfied. Jacobi method is satisfied. Now second is, you see in this case A11 is 0 and A22 is 2. Now you see the diagonal entries, one of the diagonal entries is 0 and one is not. So condition 2 is not satisfied. So what do we do? We interchange the rows. Let's say this is my system 1. We interchange the rows of A and write a new system as 1, 2, 0, 1. Here you will have x2, x1, and then you will have b2, b1. So note that for system 2, both the conditions of Jacobi methods are satisfied. Both the conditions of the Jacobi method are satisfied. And what is the fourth thing? You see, system 1 and system 2 represent the same set of equations. Okay. See, if you write down the equations, system 1 and system 2 will have the same equations, just first equation will appear as the second equation and the vice versa in both the systems. So it means if you obtain solution of one system, then we have a solution of the other system. But what is the advantage over working with system 2? That it satisfies both the conditions of the Jacobi method. So now let us see the Jacobi method. You see, if I just copy paste it here, because I will be needing this. So we have this system of equation. Now this is finished. Yeah. So let's call it algorithm for Jacobi method. Yes, if you have any doubt, please ask. Just a minute. Yeah. So what do? You just you extract the first value x1, and see, you can write it as b1 minus a12 x2 minus a13 x3 minus so on and so forth a1n xn, and this will be minus 1 upon a11, right? Now see, this is well defined. This is well defined because a11 is not 0. That is the second hypothesis, that is the second condition for the Jacobi method. Now similarly, what you do, you can write x2 as b2 minus a21 x1 minus a23 x3 minus this by a22. Now you keep on doing that and you will get final will be bn minus an1 x1 minus an2 x2 and an n minus 1 x n comma n minus 1, this by a n n. Okay, you write. You can always do this. And then what do? So this is step 1, let's say. Step 1. Now what is step 2? Make an initial approximation of the solution. Any approximation you want to make, you just make. And we call this, let's say, x1, x2, xn. This is our initial approximation. And substitute these values of xi's into the right hand side of the rewritten equations. To obtain the first approximation. So after this, see now what did you do? You wrote x1, x2, xn in the step 1. You make an initial approximation and put these values in the step 1, and you will get some new values of x1, x2, xn. So this is what has been happening. So after this procedure has been completed, one iteration has been performed. So yes, so in the same way, repeat step 1 and 2. Okay, in the same way, the second approximation is formed by substituting the first second approximation is obtained by substituting the first approximation's value into the right hand side. Into the right hand side of the above equations that we have rewritten. So you continue doing this process. So you start with an initial approximation and put this value in step 1. You will get the first approximation. Okay. Now again, let this be x0, x10, xn0, initial approximation. Now after this, you will get another approximation. When you put these values, yeah. So what will be x1? So you just put the initial approximation in the first step and you will get the first approximation. And same in the last. Yeah, there is this last. So you just put, so your first approximation will be this, x11, so this is my first approximation. Yeah. Now you continue doing these steps and you will get the second approximation. So yes, so this is what has been written here, and you keep on doing this by repeated iterations. You will get a sequence the first solution, then the second solution, the second approximation, and you keep on doing this. So you will get a sequence of approximations that converges conditionally. So what are the conditions? We will see maybe in the next lecture. To the original solution. Okay. So okay, let us see some example. If I want to solve this system, minus x2 minus 7x3 equals minus 1, 2 and 3. So what do you do first? We write this system as, see, all the diagonal entries are non-zero, right? And you check that. So A in our system, the coefficient matrix A. So what is the coefficient matrix? What is the coefficient matrix? It is A equal to 5, minus 3, 2, minus 2, 9, minus 1, 3, 1, minus 7, right? And see, all the diagonal entries are non-zero. So this is one diagonal entry, this is second diagonal entry, and this is third diagonal entry. And what is determinant of A? So what is determinant of A? You just compute. It will be 5 plus 1 plus 2. I am just computing directly. You just try. So it will be 5 into 64 plus 2 into 19, right? Minus 3 into 15. Yes, let us compute this. I'll use calculator. 64 into 5. So this is 313, I guess, but this is non-zero, that is guaranteed. So you just see that this determinant is non-zero, hence both the conditions of Jacobi method is satisfied. So let us extract our x1 from here. What will it be? It will be minus 1 by 5 plus 2 by 5 x2 minus 3 by 5 x3. Now x2 will be 2 by 9 plus 3 by 9 x1, then minus 1 by 9 x3, and finally x3 will be, in this case it will be minus 3 by 7 plus 2 by 7 x1 and then minus 1 by 7 x2. So this will be our step 1. Now let us make some initial approximation, because we do not know the solution, so we need to start somewhere. So let this be our initial solution. 0 0 0. This is our initial approximation. So this is the initial approximation. So yeah, so what will be x1? X1 will be this where these are computed as follows. We know you just put this value of 0 comma 0 in the let's say 1. Okay, so your x11 will be okay, yeah, so this is our first approximation. So x1 will be minus 1 by 5 plus 2 by 5 x2 0 minus 3 by 5 x3 0, and if you compute it, it will be minus 1 by 5, right? Okay, otherwise it might confuse. So let us write this as x1 0 comma x2 0, because we have denoted this above also. So basically this means 0 comma 0 comma 0. We have chosen our initial approximation to be this. You can choose anything, but choosing 0 0 0 is a suitable easy choice. Now let us compute the others also. So here you will have 0 0, so you will get 2 by 9 as x21, and x31 will be, yeah, minus 3 by 7. So this is our first approximation. What is the first approximation? It is x1 is minus 1 by 5, 2 by 9, minus 3 by 7, and this is precisely, you know, which is approximately equal to minus 0.2, 0.222 and minus 0.429. Okay. Now how will you take the second approximation? It's nothing, right? You just use these equations again and again with the new values that are coming up. So I will use these equations again for the second approximation. For the second approximation, we put x1, these three values, x1 1 and this x2 of 1 and x3 of 1 in 1, right? So we will get then x, the second approximation we will get by putting these values. So if you solve it in the second approximation, you will get somewhere around 0.146, then 0.203, and then minus 0.517. So our second approximation will be 0.146, 0.203 and minus 0.517. Yeah, so this is the Jacobi method, and continuing this procedure you can obtain as many as approximations do you want. Yeah, so okay, so you keep on doing this, then you will have, for example, yeah, so I'll just make a table x1n, x2n, x3n, right? And here is the value of n. So at 0 we took 0, 0, 0, right? Now when x11 is 1, n was 1, we saw it was, what was it? It was 0.2 minus 0.2, then 0.222 and minus 0.429. In the second, we saw it is 0.146, 0.203, minus 0.517. Now you keep on doing this. I have performed some calculation and I would like to share it with you. So third approximation will be 0.192. I just want you to see one thing. This will be this. Then fourth approximation will be 0.181, 0.329 and minus 0.424, 421 Then fifth approximation will be 0.185, 0.329, then minus 0.424, okay, just a minute. Here you have 0.424. Yeah. In the sixth approximation, you will get 0.186, 0.331 minus 0.423, and in the last you will get 0.186, 0.331 minus 0.423. Okay, now you see, maybe I'll just put this a few inches here. Yeah, now I have some space too. Yeah, because these entries are minus you see in the last column, see in the last two columns, the answer is almost identical, right? You perform these iterations and at the seventh stage you will get this. So what does this show? So it shows that the last two columns in the above table are identical. So one can conclude, therefore one can conclude that to three significant digits the solution is this. This is up to, see, remember, up to three significant digits we are seeing. Now for the linear equations in example 1, for the linear equations in this particular example, we saw that after a certain stage the answer is turning out to be same, and in this case we say the Jacobi method is converging. That is, after repeated iterations one is getting an approximations that is correct up to certain significant digits, and they are appearing again and again in the subsequent approximations. And this is a part of a much more general iterative formula, okay, general iterative method, that they tend to converge to the real solution, they tend to converge to the actual solution given some conditions. Okay, now if you want better approximations, okay, then you have to take as many as iterations you want for the better approximations. Okay, now see, one thing I would like to share in this method is the following, because that will set the stage for the Gauss-Seidel method to come. When we rewrote this system in the form of the step 1 of the Jacobi method, you see, Okay, I will rejoin again. Something is happening. Yeah. So here, what does happen? You obtained x1. Okay. Let me just explain what I want to say. Let us go to the Gauss-Seidel method. The Gauss-Seidel method. It is a modification of the Jacobi method. And see, this modification is no more difficult to use than the Jacobi method, which means it is a better it will give you better approximations than the Jacobi method, but at the same time it is as easy as the Jacobi method to compute. So, like with the Jacobi method, what did you do? Let me just write. With the Jacobi method, the values of xi obtained in the nth approximation remain unchanged until the n plus 1th approximation comes, right? I think I can write it this way: until the n plus 1th approximation has been computed. And this is true, right? We just saw in the Jacobi method first happened. For example, in the first approximation we will use, though, like for example in this step, you just take this step. We have already computed the value of x1 at the first approximation in this step, but in the next, for computing x 2 of 1, we are again using x1 of 0. We could have used here x1 of 1, right? Because we already have this value by the first step. And this is precisely the Jacobi method is. Yeah. So with the Gauss-Seidel method, we use the new values of xi as soon as they are obtained. We use the new values of each xi as soon as they are known. So this means as soon as, yeah, that is the key point. Okay, this means once you determine x1 from the first equation, let's say x1n from the first equation, then use this value in computing x2n and so on. Okay, so I'll just I'll just tell you what I'm saying. So you see this x1, what do? You first take an initial approximation, right? Call it x superscript 0, and it will be this is our initial approximation. Now in the Jacobi method, let's go to Jacobi method. How did we obtain the first approximation? Yeah. So see, for the first approximation, the value of x1 is same, but see, when you're, so this you take same, this you write same, but when you go to x1, you don't use this value anymore. You use the fresh x11 value instead of x10, and because in this x30 and xn0 they are still not known, so we won't be using them. Now you keep on doing this, and then in the last step, see, this x11 is known, x21 will be known, and this will also be known. So in the last step you use the fresh value. Okay, so the Gauss-Seidel method is like, you are eating as soon as the cake comes out of the oven. In that sense it is true. And similarly you compute the the second approximations. So example, we continue this example what we just saw, this example. Okay, how do I, just a minute. Because first approximation will be same. Yeah, so we continue with this example, but in this example now what we'll do, we'll apply the Gauss-Seidel method. So again, as we saw, we can apply the the assumptions will be same. Okay, the assumptions will be same. So we have this, and let's take this as our initial approximation, and in this case, the first approximation will be same, right? It will be -1/5 plus 2 by 5, x2 0, right, minus 3 by 5, x3 0, and it will give you minus 1 by 5. But see, the difference will come when you go for the next entry. It will be 2 by 9 plus 3 by 9 x1. We used this in the in our Jacobi method, but now because we know what is x11, we will use this value. Okay, we will use this value because x3 0, x3 1 is not known, so we will have this. Like we will not change the rest. So then it will be so it will be 2 by 9 plus 3 by 9 times minus 1 by 5 minus 1 by 9 times 0, and approximately it will be equal to 0.156. I think my computations are correct. And what will be x3 1? It will be minus 3 by 7 plus 2 by 7, x1 not 0, now it will be 1, minus 1 by 7, x2 not 0, again it will be 1. So if you compute this, it will be 2 by 7 minus 1 by 5 and then minus 1 by 7. What is x21? It is 0.156, and approximately it will be equal to 0.508. So the first approximation is the first approximation is actually x1, it will be minus 0.2, 0.156 and minus 0.508. Oh, I forgot one minus sign here. Yeah, and now if we draw the table, if we draw the, so much like this, we will draw another table. So yeah, so you keep on doing this iteration and we will get a table. Yeah. So let me quickly write my calculation. So it will be something of this form. I am just filling the table, so maybe hold on for a while. Yeah, so with this, again see the same thing as we see in the Jacobi method. So what was the Jacobi method? In the last 6th and 7th iteration, the values started to stabilize, but see here you need only 5 iterations, right? So in this way, so note that only 5 iterations only 5 iterations of the Gauss-Seidel method is sufficient to achieve the same accuracy, and this is an important note, okay? So same accuracy as was obtained in 7 iterations of the Jacobi method. So here you need only 5 iterations of the Gauss-Seidel method, right? But here in the we saw that same example, when we applied Jacobi method we needed 7 iterations. So this somehow gives a hint or an intuition that Gauss-Seidel method is it works finer than the Jacobi method, and it should be clear from the algorithm. Why? Because at any stage, at any point in time, we are using the fresh values as soon as they come. Okay. Now the question is, do this, if I start with an arbitrary, in both of these method, you have to consider an initial approximation. So a good question might be, can we start with any initial approximation and still be able to recover the solution? The answer is no. Okay, and that is where in the beginning I was saying the methods converge conditionally. Now we will see an example of a system of equation where these methods diverge. In the sense, you are starting with an initial approximation, but it is still not giving you the correct answer. So let's call it an example of divergence. Let us consider this x1 minus 5x2, 7x1 minus x2, and let this be minus 4 to 6. Yeah. So we apply the Jacobi method here. We apply the Jacobi method using the initial approximation (0, 0). Using the initial approximation x0 to be 0, 0. If you rewrite this equation, in the form of step 1 of the Jacobi method, and you will get x1 to be minus 4 minus 5x2 and x2 to be minus 6 minus 7x1. Oh, sorry, plus x1. Yes. So it is easier to see this x1 of 1 will be, this is first approximation. It will be minus 4 times 5 x2 0 then it will be minus 4, and x21 will be minus 6 plus 7 times x10, and it will be minus 6, right? Now you compute the second approximation. It will be minus 4 times 5 x2 of 1, which will be minus 4 minus 5 times minus 6, which will be 30 minus 4, 24, right? Oh, 6 oh sorry, it should be plus, right? Here it should be plus. Yeah. So then you will have minus 34 here, and then you see x2 of 2, it will be minus 6 plus 7 x2 of, oh sorry, x1 of 1, and you will have minus 6 plus 7 minus 4, 7 चौक 28 और 6, so it will be minus 34 again. You continue doing this and we get the iterations as and you will obtain this table n x1n, this approximation table. We took when n is 0 to be 0 0. For 1 it came as minus 4 minus 6. For 2 it will come minus 34 by minus 34. For 3 it will be minus 174 minus 244. For 4 it will be minus 1244. For 5th minus 6124 minus 8574. So you see this, as you keep on having the approximations, iterations, you see the answer, the approximations is getting bigger and bigger and bigger. Now let us see how far they are from the original solution. The original solution will be, what will be the original solution of this? You just solve it directly. You can solve it via Gauss elimination method or anything. So it, x1, x2. It will be A inverse. What is A? A is 1 minus 5, 7 minus 1, right? This inverse and minus 4, 6. So what will be the inverse of this? You just interchange. For 2 cross 2, computing inverse is always easy. And you divide by the determinant. And what is the determinant? Minus 1 plus 35. So it is 34, right? Determinant of A is 34. Yes. And you multiply it with this. So what are you getting? Minus 4 plus 30 and then 28 plus 6. See, 1 comma 1 you are getting the solution. Oh. So 1 comma 1 is actually the original solution. But see, here you are getting far and far from that. This will never converge to this solution, right? This sequence. Yeah, you see, this is, it does not converge, let alone converge to 1 comma 1. The original solution is this 1 comma 1. This is the original solution okay. So you see the original solution is 1 comma 1, and for this particular system of linear equation, you see with every approximations, with every successive approximations given by the continue, what I am writing here, sorry, yeah, with every the approximations given by the Jacobi methods becomes progressively worse, okay, instead of getting better. So we conclude that in this case the Jacobi method diverges. So therefore the Jacobi method diverges. Now the question is, what about the Gauss-Seidel method? Does it also diverge? The answer is yes. The answer is yes. Okay. So let me just write few line. Note. In the above example, the problem of divergence is not resolved by using the Gauss-Seidel method. Using the Gauss-Seidel method. In fact, using the Gauss-Seidel method rather than the Jacobi method, if you use Gauss-Seidel method, in fact, the approximation becomes worse. In fact, for this particular system, the Gauss-Seidel method diverges more rapidly. We will see. As shown in the table below. Okay, let for example, the Gauss-Seidel method diverges more rapidly. So if you are using, the Gauss-Seidel method, what you will get in the, okay, how many okay, yeah. So in the Gauss-Seidel method, for the 0th approximation, you start with your initial approximation as 0, 0. And your first approximation will be minus 4, minus 34. You see, in the here the second approximation was minus 6. It's starting getting worse, right? Because the solution is 1, 1. So we are getting far and far from 1, 1, which means we will not get the original solution. Minus 174, minus 1224. The third will be minus 6124, minus 42784, and so on and so forth. See, even in third approximation as compared to the fifth one, we are getting, the worse approximations. Yeah. So the question is, in this particular example, simple to solve. You see this. Okay, let me just join the meet again. So somehow my system is facing some issues. Yeah. Yeah. So in this example, what is there on the screen? We saw neither the Jacobi method and nor the Gauss-Seidel method helps. So what to do? So the question is, a natural question is to study under what conditions these two methods will converge to the original solution. Okay. So we will see that whenever A is a strictly diagonal dominant matrix, we see that these methods will converge. Remark. We will see for a special type of matrix, for a special type of matrix A, which we will call strictly diagonally dominant matrix. These two methods, will see that this will always converge. These two methods will converge. Now, what do we mean by a strictly diagonally dominant matrix? It means, okay, let me just write down the definition. Strictly diagonal dominant matrix, when mod A11 is strictly greater than the absolute value of the sum of the other entries in the row. So which means the diagonal entries not only has the highest modulus, it has the modulus greater than when combined the other entries of the row. This is the definition of the strictly dominant diagonally dominant matrix. See, in this example our A was this. This was our A. 1 7 minus 5 minus 1, right? And this is not a strictly diagonally dominant matrix, right? This is not at all a strictly diagonally dominant matrix. But if we interchange the rows, it becomes strictly diagonally dominant matrix. Am I correct? Okay, let us, example. If we write this system, 3x1 minus x2 minus 4, 2x1 plus 5x2 is 2. Now you write this system, the coefficient matrix will be 3, 2, minus 1, 5. And you see, this is a diagonally dominant matrix, right? Because mod A11 is 3, which is strictly less than, because it has only one entry other than this, so it is 1. And what is mod A22? It is 5. And it is strictly less than mod A21, which is strictly greater than mod A21, which is 2. So therefore A is diagonally dominant. So if you apply Jacobi method or Gauss-Seidel method on this system of equation, and you start with any approximation, let's say 0 0, then this method will this will make sure this diagonal dominance of this matrix, coefficient matrix A, will make sure that your method converges to the exact solution. And what are the exact solution? I think this is minus 3 and 1 for this. You see, you just check, okay? What about this system? What about this system? Four x1 plus 2x2 minus x3 equal to minus 1, x1 plus 2x3 equal to minus 4, 3x1 minus 5x2 plus x3 equal to 3. You know what will be the coefficient matrix? See, the coefficient matrix A, it will be 4, 1, 3, 2, 0, minus 5, minus 1, 2, 1, right? Now you see, are these diagonally dominant? I think these are. You just check. Is it? See, this is not a diagonally dominant matrix, right? Is not diagonally dominant. Is not strictly diagonally dominant, right? It is not. Why? You see, because mod of A22, which is 0, and it is strictly smaller than mod of A12 plus mod of mod of A21 plus mod of A23, which is 1 plus 2 and 3. However, you know this, however, if you interchange, if we interchange, let's say this system was Ax equal to B. If we interchange the second and the third row, we know this system, you know, let's say A tilde, it will be 4, 2, minus 1, then 3, minus 5, 1, and then 1, 0, 2. And let's say this is my unknown vector x. and we'll change b tilde also, because we have interchange first and second, so here also we'll interchange second and third. Sorry, in A we have interchanged the second and the third row. In B also we will do that, so that it represents the same system of equation. Yeah, and here we will do x1, x2, x3, right? Or some other variable, maybe y1, y2, y3. Now these two represents the same system of equation. Just a minute. Yeah, here also you write some y1, y2. Yeah, so these systems, we have not changed the system, but see, the good thing is now we have a diagonally dominant matrix, you see. So sometimes if A is not strictly dominant, because we know interchanging rows and interchanging two rows does not change the solution, does not change the system. What does a row interchange do? If you're interchanging third and second row in the augmented matrix, then it means you're interchanging so you do that also on the right hand side vector. And when you do that, what you have done actually is you have just written third equation on the second number and the second equation on the third number. Okay, so this does not harm in any way the system that you're trying to solve. Okay, yeah. Okay, so let's call it example 3. So in example number 3 we saw a case where Gauss elimination and let me just label the examples. Yeah, example 1, example 2, example 3. So in this example you saw this matrix was not diagonally dominant, right? But if you interchange the row, you see, we'll see this. Copy. Let's call it example 4. Example 4. Same example, interchanging rows to obtain convergence. So this is the same example as as we saw in So if we interchange rows, what does it mean? You just write this as 7x1 minus 7x2 equal to 6, x1 minus 5x2 equal to minus 4, and you can write your system in this form: 7 minus 1, 1 minus 5, then x1 x2 times 6 minus 4. Again the solution is 1 1, right? Because we have not changed any system, we have just interchanged. The solution is 1 1, and here also the solution is 1 1, and we know why, because we have not done anything. We have just written equation 1 as equation 2 and equation 2 as equation 1. But what is so in this case we saw, in this case Gauss-Seidel and Jacobi method diverges, right? Now here what we do, you see this. Now we have a diagonally dominant matrix. This coefficient matrix the coefficient matrix is strictly diagonally dominant. Okay, now let us solve this system and see whether or not the Gauss-Seidel and the Jacobi method converges. Okay, so how do we do it? Let us first see the Jacobi method. And this is probably the last example. So how will you write in the step 1 algorithm? You will write x1 to be 6 by 7 plus 1 by 7 x2, right? And x2 you will write it as 4 by 5 plus 1 by 5 x1, right? So you just choose an initial approximation, x0 to be x1 x1 0 comma x2 0. Choose your initial approximation to be 0 comma 0. Yeah. Now what will be your first approximation? It will be 6 by 7 plus 1 by 7 x2 0, which is 0, so it will be 6 by 7, which is approximately 0.8571. Yes, and sorry, and the second entry in the first approximation, it will be 4 by 5 plus 1 by 5 x1 0, and again it will be 4 by 5, which will be 0.8. Yeah, so it will be 0.8 something. So this is our first approximation. The second, let us see, x1 of 2, it will be 6 by 7 plus 1 by 7 x2 of 1, which is 6 by 7 plus 1 by 7 times 0.8, and it will be 6.8 divided by 7. So you will get 0.9714. See, already you see the solutions are coming approximately nearer to 1, right? And here you will have 4 by 5 plus 1 by 5 x1 of 1. So you will have 4 by 5 plus 1 by 5. What is x1 of 1? It is 0.8571. And this value will be, it is 0.97502. Okay, let's compute the last, we'll just compute the three. It will be 6 by 7 plus 1 by 7 x2 of 2, and if you compute it, it will be 6.97502 divided by 7. It will be 0.9964, and it will be so x1 of 2 0.1. So here you will have 0.99428. Okay, let us see what happens. Okay, let this be the last. I just want you to realize that the solutions are getting closer and closer to 1. Okay, so if you compute this, this will be you will get 0.9991, and you will get here 0.992, and if you compute the fifth one similarly, what you will get is the following. You will get 0.9998, and here you will have 4. Yeah, so if you draw the table, the table is actually a lot safer. It tells us so many things. So let us draw. If you choose your approximation initial to be 0, then the first stage you will get 0.857. Okay, we will just write 3 significant digit. Now 2, on the second stage we got 0.971 and 0.975. Third we got 0.996, then 0.994. Fourth we got 0.999 and again 0.999. Fifth we are getting 0.999 and 0.999. You see the system, like you see in the last two approximations up to 3 significant digit, the system is giving the same answer. The approximations are giving the same answer, which means like these methods converge. And where does this sequence converge to? This sequence converges to 1, 1, right? 0.9999 something will converge to 1. Now let us see what happens with the Gauss-Seidel method. The Gauss-Seidel method for this particular example also. So again choose your initial approximation to be 0 comma 0. Okay, let me just copy this. Yeah, same question. Same question. You just take your initial approximation to be 0 0. So the first entry will be same. You will get 0.8571, and here you will get 0. Now we have to use the fresh approximation. So here it is 0 1. So if you solve this, you will get 0.9714. Yeah. Now x12 of this will be 0.9959, but again you will have to use the fresh as soon as it comes, so it will be 2, and you will get 0.992. Okay. Now if you draw the table again, you continue doing this. I have shown you for the Jacobi method. So for 0th approximation you will get 0. For the first approximation, you see this we got 0.857 and 0.971. In the second approximation we got 0.995, and here we got 0.999. In the third it gets better, 0.999, and it will give you 1.000. You see, the fourth will give you 1.0000, and see, this is the final answer, right? Now if you keep on doing this, you should only get 1.000. So if you compare the table of 2, so yeah, just one line here. From here you can conclude that from this table in the Jacobi method, one can conclude that the solution is 1 1, right? Then we went to the Gauss-Seidel, and you see, if you see that these two tables together, you will see both of them are converging, and as it was bound to happen, this Gauss-Seidel method converges faster than the Jacobi method to the original solution 1 comma 1, right? Here also you can conclude, right? Here also you can conclude that one can conclude that the solution is x11 and x2 equal to 1. But note that Yes. Note that, you know, in the for the above example, you see the Gauss-Seidel method method's approximations faster, sorry, what faster? Yeah, let me share my screen. This is too much trouble. Yeah. The Gauss-Seidel method's approximation converges faster than the approximation obtained by the Jacobi method, right? Obtained by the Jacobi method converges faster. And it is bound to happen, right? Like, because we are taking the newest value that comes into the picture. Yeah, so with this we finish this two indirect methods. So let us revise what we did today. Just a minute. Yeah. So in today's lecture we saw iterative methods for solving linear system. So first of all, solving a system means solving an n linear equations in n variable, and because we'll always be dealing with an invertible matrix, we know that this system will always have a unique solution given by x equal to a inverse b. Now, unlike the other two direct methods that we have seen in the previous parts, the Gauss elimination and the modified Gauss elimination, which are not useful, because not useful, it should not be said not useful, but in the sense more primitive, because it leads a lot of computation. So we have these two iterative methods given by Jacobi and Gauss, and these two methods are named after them, Jacobi method and the Gauss-Seidel method. In the Jacobi method, what do? We first assume two hypotheses, that the system has a unique solution. Now because we will be dealing with invertible matrices, so this condition is trivially true. And second is the coefficient matrix should have no zeros on the main diagonal. If it does have, then we may try to get rid of them by using the row interchange. And after row interchange, we know the system does not get changed. The equation just get flipped. Okay. So we saw the algorithm for Jacobi method. You extract x1, x2 and xn as given in the step 1. Step 2 is to make an initial approximation. More generally, we will start with the easiest one, which is 0, 0, 0, and substitute this initial approximation to obtain the first approximation given by this. Now you continue, now that you have the first approximation, you again substitute this value in the rewritten form of the step 1, and you will get the second approximation, and keep on doing that, and you will get a sequence of approximations. Now the question is whether or not this sequence will converge to the original solution or to the exact solution. The answer is no. We just have seen some examples. Okay. But in a special case, when A has a certain property, we know that this solution will converge. We might do the proof of that theorem in the next class, but for the sake of learning these two methods, we just get to know that whenever A is a strictly diagonally dominant matrix, the Jacobi method will converge to the exact solution. The order of convergence and the rate of convergence, of course, might differ, but definitely it will converge. We saw some example, okay, and computed the this Jacobi method approximations explicitly. Then next we have a Gauss-Seidel method, which is better than Jacobi method in the sense it uses the same amount of computation, but it replaces the it replaces the nth approximation with the newest value in the n-1th approximation. It does not wait until the next approximation to use the value of the previous approximation. That is the point. The formulas are same with the exception of that you use the newest value. Okay. And we saw the same example as in example 1 with this method, and you see that with this initial approximation 0 0 0 and the Gauss-Seidel method, you get a table. Of course it contains the value of the approximation, but in this table we saw only 5 iterations of the Gauss-Seidel method is sufficient to achieve what we have obtained in the 7 iterations of the Jacobi method. So we are in this way Gauss-Seidel method is a much more better method than the Jacobi method. It gives the same accuracy with the fewer iterations, and this is always a blessing. Now then the question we addressed is, as asked in the beginning, that whether or not every time the Jacobi method or the Gauss-Seidel method will give you a sequence of approximation that will converge to the exact solution. So we have this example given by x1 minus 5x2 is minus 4, 7x1 minus x2 is 6. We started with an initial approximation 0, 0. You know the exact solution is 1, 1. You just pause the screen and check. But after applying the Jacobi method, we saw that the solutions are getting worse and worse. Solutions means approximations are getting worse and worse. For example, the 5th iteration you are getting minus 6124, minus of thousands in values. So that will never converge to 1, 1, right? So in this case, the Jacobi method diverges. We saw, okay, Jacobi method diverges. What about the Gauss-Seidel method? And the situation for the Gauss-Seidel method was even worse. At the 3rd iteration only, we are getting thousands in the value, which will never converge to 1, 1. So this leads us to the question, under what certain conditions can a certain condition make sure that these methods will always converge? And the answer to the question is yes, and that condition is when the coefficient matrix A is a strictly diagonally dominant matrix. What do we mean by strictly diagonally dominant matrix? It means the entries on the diagonal will have the absolute value of the diagonal entries will be strictly bigger than the sum of the absolute value of the other entries in the row. So yeah, we then saw some example of diagonally dominant matrix and non-strictly diagonally dominant matrix. However, we saw if we can interchange a matrix, it might not always be possible, but it can always be a good idea to interchange rows to check whether or not we can obtain a diagonally dominant matrix from a strictly diagonally dominant matrix. For example, in this case, we saw that this is indeed possible. And going back to example 3, which was given by this with the exact solution 1, 1, we saw that Gauss-Seidel and Jacobi method diverges, and we just observed that the coefficient matrix was not strictly diagonally dominant. But if you interchange the rows and if you interchange the two rows, you will not get a new system. What you have done, you have just written the second equation first and the first equation on the second number. So the solution will be same, but the advantage is the coefficient matrix now is a strictly diagonally dominant matrix. And we know for such matrix the Jacobi method will always converge to the exact solution. Indeed, we saw using Jacobi method in computing explicitly that after 5th iteration the solution seems to converge to 1, 1. That is indeed true. For the Gauss-Seidel method, that is bound to happen. The situation is much better. You know, in the fifth iteration, we only get the exact solution. So, yeah. And the final note is to observe that, you know, the Gauss-Seidel method converges faster than the Jacobi method to the exact solution. So if there is any doubt, you can type in the chat box. Otherwise, yes, we are done.